I'm very excited today. Thank you everybody for attending this webinar on HALT testing. I'm doing it here with Chase Wers, who's the founder of Reliant Labs out in California. I really wanted, since he and I enjoy in our collaborations and our discussions on HALT testing, I thought it'd be really great to do a webinar for people where I talk a little bit about kind of the approaches, pitfalls, what it's about and the methodology. And then Chase can share his observations from his decades of experience and bring us through some examples, that really connect it. So he and I were very excited to put this on. So we will jump right in. First, I'll just share that I'm starting a new series called the Perfect Reliability Tools. And it's going to be a bunch of short books that are, each one's less than like 60 pages. You could read it in an hour, and each one will cover a specific reliability tool. This first one will be coming out this Friday, the Perfect HALT test. So it'll be available on Amazon. You can email me. We'll be doing a book launch webinar on Friday. So feel free to email me and I'll send you an invite to that if you like. All right, so let's just start right off with the basics. What is HALT? HALT is pretty simple when you get down to it. It's testing to fail. We're not looking to test to pass. So many of the tests, and the word test makes it to be something that we want to pass. But that's not the point with HALT testing. HALT testing is to get information about the product through making it fail. So you're doing it right if you're this kid and there's firemen involved and something smashed up and safety tape, then you're doing HALT tests the right way. We're trying to create really interesting observations to learn about the product by observing how it fails. So the formal definition from HALT testing, when it was really formalized as a reliability technique by Dr. Greg Hobbs, is it's done to ruggedize the product and obtain large margins over the expected in-use conditions, use stresses that can cause relevant failures, and the stresses are not limited to the field levels and use cases, which is really important to highlight because we are allowed to use any stress we can think of, even if it's not in any way applicable to the environment the product's used in. Because these failures and what we observe can drive robustness changes that can help in other ways. You might do a stress with vibration that then can actually help mitigate issues in manufacturing. But the actual acronym, and Dr. Greg Hobbs said this, as he didn't feel it really suited it well as he used it over time, and I agree, is that highly accelerated life test doesn't really work because one, it has nothing to do with life. You aren't looking to make any statement about life for the product. What you're really looking to do is to create failures in a very fast way. And I also think test doesn't fit very well because tests are things we want to pass. And really, this is an exploration. So in my world, a HALT test is really a happy test. So if you ever see me and come up and say that, I know that I know that we live in the same world and you get it. So we have to, right out of the gate, be willing to totally step aside from the constraints we normally have with use case environment. And this is so fundamental because as you're designing a HALT test, it's so easy to want to take the stresses and methodologies you had in other testing that you did and to apply it and use that as constraints when it's not. So you're going to hear me keep making that point over and over again because that's one of the common pitfalls that I've seen is that we limit our imagination and stay constrained within what we believe are stresses that are reasonable in the normal use case and environment. I also want to invite all of you to at any time just speak up and interrupt me and ask a question. I'm a big believer in discussion, learning through discussion. I don't think it's always great to save your questions to the end when they're not, we aren't all in that same mindset from the point when you had the question. So absolutely, just, as you're listening, if you want to ask a question, just jump right in. So I actually believe that, even though HALT was formalized as a reliability tool in the 80s, I really, in my curiosity, always in how products are developed, and having always research and looking into how different technology advanced, I found an interesting example of what I consider possibly to be really the first HALT test. And this was back in the 1960s when they were developing the Saturn V, Apollo rockets. And this was based on the Rocketdyne F1 engine, you can see there. And they were having a tremendous issue with the thruster cones cracking. And this really actually came to a point where it could put the whole program on hold. They had to deal with obviously tremendous forces, widely varying conditions, and but it had to be lightweight as well. And they had, only limited materials they could work with. And so the breakthrough came when an engineer suggested they simply put dynamite, black powder charges, on the cones and blow them up and shatter them and see how they break, and using that information and observations to help them make a better design. And this worked so well that within a very short time period, they designed a cone that not only didn't crack, but could self-dampen out any natural resonances that occurred in flight. And a lot of these, design best practices are still used today in the thruster cones you see in all rockets. So that is exactly the HALT philosophy, to, instead of doing repetitive testing with the normal thrusting forces, and in that case, it was very expensive and very time consuming, simply put dynamite on it and blow it up so you can look at the pieces of it to get a better understanding of how that design works and doesn't work. So the process of HALT, it's in 4 steps. We start by stressing the product. We start low and we step the stresses, because if you were to put, let's say, too much dynamite on the cone, you might blow it apart to such a degree that the failures and initial cracks that were of most interest will no longer be easily observed. They'll be amongst way too many pieces and being shattered to way too much of a degree. So you'll see that when we select stresses, we tend to apply them in stepped increments. We then are going to make sure we're able to observe failure. So typically this means we need to be able to operating the device, if we can, in a way where we can monitor that some response is happening. It's no longer performing as intended. When we have these observations, it's great to be able to stop the test and to analyze the observed failure or performance issue, because this is where we're getting those really valuable ingredients to help us make a more robust design. Then what we look to do is, if we can, within the actual testing cycle, improve the design or make changes to help us understand what could make the design perform better, we do it. So that then as we continue the cycle, we are, within that one testing time frame, potentially even having what are validated directions for design improvement. But sometimes that cycle happens over multiple tests, where you come away from a 3-day sessions of testing, you have your opportunities to make your design improvements, and you come back and do it again. So the cycle doesn't just happen within one testing session. This can be the cycle that's throughout your entire product development program. So the HALT stresses that, we typically start with, if it's, kind of a common, electromechanical device, is we look at temperature extremes. That's a great way to see how a product can fail, or dramatic temperature ramps, which cause very dramatic thermal expansions that can cause a lot of mechanical stress. We do vibration extremes, and we do combined stresses. But you have to remember, again, we're not limited to these. It really can be anything that you think of. So you'll see with HALT chambers that one of the things that makes them unique from other types of testing equipment is that they use liquid nitrogen. And liquid nitrogen, as opposed to using compressors, is key because of the fast temperature transition rate that we need. Not the temperature extremes. Compressors can get down very cold. It's very quickly transitioning, because you get tremendous mechanical stresses if something has a large thermal mass and there's a temperature gradient across it, or if you have dissimilar materials in contact with each other. With the vibration, another important characteristic you'll find with HALT chambers is they do multiple simultaneous broadband frequency in 6 axes. So how does this differ from other vibration tables? Well, a lot of other vibration tables use a set frequency, a lot of times that you can sweep in a single axis. And they're usually called electrodynamic vibration. And that's because it's very much like a speaker, a music speaker, where you have an electromagnetic system that actuates in a single axis and you can control the frequency. And this is a great tool, but this is a great tool for investigating failures. That's typically when I use it, when I have a failure and I want to investigate it with vibration, and I can sweep frequencies, lock in on frequencies, and change orientations. You have to remember, HALT's about violence. The HALT vibration, we're looking to do more like replicating that dynamite strap to the rocket cone, where we just want to put as much energy in there as possible. So we look to put multiple frequencies in simultaneously and have it be in all 6 axes, the 3 linear axes and 3 rotation axes at the same time. So to do this, HALT chambers typically have a pneumatic hammer type system that are set to a very specific type of table that transmits the vibration. It doesn't ring at one frequency. It allows a lot of different frequencies to transmit. And they're at very specific orientations and actuating to a controlled degree for how many Gs of force you want to put in. So on the thermal side, we do both the hot step stress and cold step stress. And with these, the methodology is we are looking to continually increase per set steps, maybe 10 degrees C, and then observe if the performance has changed. And if we see the performance have changed, we back off, by a step or two and see if it recovers. If that's the case, it's a soft fail. And then we may then continue until we get a hard fail, where when you remove the stress, it no longer can recover. Sometimes when you get a soft fail, you'll isolate that area, maybe in this case, with a hot step stress, you'd put a bit of cool air on that one part so you can progress farther and see other soft fails in other part of the product. You use the same technique with the cold step stress. And so you're going to learn a lot about what happens in these extremes. And this information isn't just great for the HALT and making the design more robust. These outputs can be great for better ensuring that if you have hot and cold extremes in your use cases, how much margin do you have on that? Or taking this and using just the hot and cold step stress with many units and see what manufacturing variability does to these. So these individual steps can, after you find information that's of interest, use these steps in other types of tests to further explore. And then, as I mentioned, you have the rapid thermal. So once we learn about where the soft fails are, we can do transitions very fast within that range to see how the thermal expansion and contraction affects the product. How many of these cycles can it take and to what range before you see some kind of failure? And this is really, effectively mechanical stress. So what does HALT do? It quickly discovers the failure modes. It evaluates the design margins, supports release of a mature product. This is a very fast test. I mean, a lot of these can be done. Each round is within 3 days, providing a tremendous amount of input to help you in the super short time frame you have with a product development program to make better design changes early when they're easier to make. So this can really reduce your development time and cost, and the ROI is so high that quite often, once people experience it, it becomes a standard part of every product development program. And you have to remember, it's not something you try to pass or fail, and it's not a tool for discovery of design characteristics. This is really just about learning about failure modes. So remember that kid? What does that kid want to be? Well, if we look again with that idea of test to pass versus test to fail, and test to pass, the objective being to measure something. We have lots of reliability tools that measure. And test to fail being about to learn, this kid wants to be a detective. That's what it's about. It's about creating a crime scene for your product and being a detective to understand more about the design, how it works, and how it responds. So that's the mindset we want to make sure that we stay in. So this is a graphic I've created, which has 2 parts to it. One is the bathtub curve, which many of you are very familiar with, where you have a curve that is a composite of quality failures, stress-related failures, and wear-out failures. And quality failures are very dominant early in the product's life, which is why we offer our customers warranties, because it's very likely that if a product is made incorrectly, the failure from that will occur, relatively quickly. Then we have the stress-related failures, which are dominant during use life. And typically when we say reliability in a generic way, that's what we're talking about. As they use it, what's the likelihood of failure can occur? Then later we have wear-out failures. And wear-out failures, I don't even like to call them failures. I mean, that's how the end of a good product, its life ends. And they're not really failures. It's a design characteristic. This is when the design, is expected to wear out under normal stresses, and it's very predictable. But you'll see at the top here, I put, again, that measure and improve. I put a gradient line up there showing, for each of these 6 types of reliability tools, each one has its own unique blend and objective between measure and improve. And the reason why this is really helpful is because you can see I put HALT testing all the way down on improve. It really offers very little in measure. You can use some of the steps to do measurement later, but that's not the point of HALT when you're doing HALT testing. You're really allowing yourself to disassociate from measuring anything so that you can get the information optimized to get the information you need to improve the design as quickly as possible. And this is why, again, you come back to that, I'm okay stepping away from use case and other constraints I would need to know I'm measuring something accurate. On the other end is accelerated life testing, right? And accelerated life testing is really almost entirely about measuring. It doesn't offer a lot of information for improve. You use this when you're trying to characterize the wear-out failures and to understand when end of life is going to come for a product that did not fail for another reason earlier in its life. So you can see those two extremes, and you have reliability growth, which really can do both equally, within its part in the product development program. So if we look at HALT, HALT can improve all 3 areas here. Now, I call it blind robustness improvement often because, we aren't measuring it against a use case. We don't know how much what the changes we're making are going to improve it. But we do know it's going to improve it because we've gotten a chance to observe a performance issue that now is input in our minds, our creative minds, for improving the design. So you do always find great improvements that you can do, a lot of them very simply, really without great cost. They're changing simple design features, but we know we are improving the design. So the fact that it can help the entire bathtub curve is very powerful. So what it'll do is it'll reduce the random failures during life. It will shrink that time period you have manufacturing, variability causing quality issues, and it'll push out that time to end of life simply because you are adding robustness across all the features and how they relate to the stresses they experience, including the stresses of manufacturing variability. You just simply will have more margins. So where do you use HALT in the product development program? As many times as you can. It can be helpful even before you have your first prototypes. You can sometimes fabricate something that has the key characteristics or modify a legacy design and do HALT testing on that, because the earlier you get that feedback from HALT testing, obviously the quicker you can make changes, because as you continue through the product development process, it gets harder and harder to change the design. More gets locked in. So don't feel like you even have to wait for the first prototype if you think there's some kind of assembly you can get that will provide some interesting information. When the product gets to the point of being integrated into the higher level system, it's great to do it again, because you have to remember other things have changed around it and it may act differently within the bigger system. So we're going to look for opportunity after opportunity of where we can use it. Now, how does HALT connect with a lot of the other tools in the product development program? It connects in a lot of ways. HALT testing can be a great action item coming out of an FMEA. In an FMEA where you're assessing risk and failure modes, a lot of times you find that, okay, this failure mode has a very high severity. And actually, we're surprised at how likely it could be. Can we investigate if there's a way to induce this failure mode and see if we can make simple design changes to reduce that likelihood or reduce the severity? HALT testing, it'll provide that information. Design of experiments. And HALT testing can be great because you're getting to learn about the relationship between stresses and failure modes, which is the entire focus of design of experiments. And then HALT testing can help with root cause analysis. You can find things there that then inspire you to do specific root cause analysis you may have not done otherwise. It also is a requirement if you're going to take your manufacturing quality process all the way up to the level of HAS, which is the highest level of screening, you have to have HALT output for that. So it connects with and enhances many other parts of the product development program. So I feel that there's 4 stages of emotional acceptance of HALT. Typically when I first introduce the topic to individuals and designers, they say, don't tell me my baby's ugly. Of course it's going to break. They've spent so much time trying to have their design work, trying to have it pass tests. Of course, they don't want to see you just effectively be violent with it and show the world how it doesn't work. But you might drag them kicking and screaming into it. And then in the second stage, they're in the HALT test and they'll be like, wow, I didn't expect that to break that way. That's really strange. And it inspires them to start thinking, about the design, and they start getting ideas. And then they all of a sudden find themselves making a better design quicker. And it's always the same people that were most passionate about fighting it that come back first in the next product development program saying, hey, could we do HALT again? I want to do it right away because it gave me so many good ideas. So I always am greatly entertained by watching that, process, the 4 stages of acceptance occur as engineers get to do this for the first time. So you want to remember with HALT, it's this kid. This kid gets it. This kid's all about just making a mess and getting to see what happened. And this kid too, I love it. This is one of the things I love about reliability engineering. So hopefully that's you as well. So are there any questions on those topics that I just covered?
Hey, Adam, this is Andre.
Hi,
I
Andre.
have a question and a comment. Let me start with a comment. It's kind of interesting that you mentioned at the beginning that HALT is not really a HALT because it's not a live test. It's not really a test. Because some time ago, we developed something we actually christened RFMPT, which stands for Rapid Failure Mode Precipitation Testing. Although we still kept the word testing in there, but the idea was we know that one of the shortcomings of HALT is actually the vibration profile. Even though it gives you all 6 degrees of freedom, it still it has a usually pretty high high frequency content, and at least with the products I've been working with, we saw lower frequency content, and we had a certain vibration profile. So basically, we kind of combined electrodynamic shaker with the temperature chamber. This way, we actually were able to recreate the shape of the vibration profile. But what we've lost compared to HALT chamber is this fast transition you were talking about because of liquid nitrogen. So just like I said, just a comment. So we not changed the name, but came up with something a little bit different than HALT, which also gives you an opportunity to do HALT. I kind of joke HALT without HALT if you don't have equipment, because I mean, not all the labs actually have HALT chambers.
Yeah.
So that was my comment. My question is, with electronics development, what I found where you were trying to basically use HALT is that the product is not ready basically to be halted, so to speak, because you need, like, to do HALT properly, you need to have a fully functional and be able to monitor the unit. At least that's true for electronic units. And I think HALT is used, not mostly, but quite a bit for electronics. So the question is, how do you balance that? Because I've seen kind of things I consider ridiculous where a customer would be saying, okay, we need to have a HALT as part of the basically kind of validation testing at the end of development cycle. And, it doesn't make any sense, because that's validation testing is basically where you need to prove that your design is good, but
Right.
HALT kind of gives you something else. So the question is, just to make a long story longer, how do you how do you manage that? How you balance this thing, product readiness and being able to do halt and still basically get something useful out of it?
So is your question, how do I incorporate the halt, per the constraints you just described, or how do I help that customer understand how halt does not do that kind of validation in the end?
No, the first one. Yeah, I mean, explaining. Yeah, we're usually pretty good at explaining this.
Yeah.
But the thing is still, if you want to do halt and your product is not fully functional, you don't have the latest software, you don't have a cable, you don't have a connector. Uh, how do you balance this? How
Yeah.
you can make this process, I mean, halt as early as possible without losing basically its benefits?
Well, the thing is that you have to remember that we're not looking to make statements, so you don't have to qualify it as the perfect halt test, right? Even though, funny enough, that's the name of the new book. I guess that's kind of ironic now. But the doing halt testing on any derivative of the technology will teach you something, right? So you're looking for, but obviously the more the product is not like your final product, the less of it you're getting to examine in the test. So it's figuring out that balance. And that's why I always encourage to do it more than one time. So if you believe that pretty soon, some programs soon after prototype, that thing right after R&D prototype goes to manufacturing prototype, and then it's like locked in. If that's the case where you have this insanely short window to have any, further design input after prototype, it would really behoove you to put the energy and time into making any versions of that design that you can quickly fabricate that maybe don't have all the features, but have a lot of the key features, or maybe the new the new features compared to your legacy products to halt test. And at least you would, at a time in the program where you can make changes, get information. Here's an example. I was working on a laser program, and the lasers were extremely expensive. They were over $2 million each. And we wanted to use HALT to try to learn, about what this new technology, this new generation they were doing, where were the vulnerabilities. But of course, they're not going to give us a $2 million laser to destroy. They basically, the first ones, the prototypes, they would do field trials with. So I sat down with the team and we spent a lot of time really looking where the risks were with the new technology. And we ended up designing our own simple little assemblies. What we ended up very concerned was the structure that was had to have hold gases certain ways, and realizing that the cracks there and things there and heat stuff and motion could cause cracks. So we made a bunch of different small assemblies that didn't even exist in the laser with the different types of welds that we were interested in and the geometry from the new design, and we halt tested that. And then we also use those for alt testing too. So we ended up creating an assembly that didn't even exist in the final product, but its response to those tests would both give us information about what different design features would make it better, and even gave us some information when we did alt testing. So in that program, where if we're never going to be given a $2 million product to destroy, and two, if they did, it was already too late to give them feedback, that was the best path.
Okay, well, that's a good solution to this.
Yeah.
Kind of go after subsystems or recreate something which would produce a similar failure mode. Okay,
Yeah,
thanks.
I mean, the trade-off is the amount of engineering time. We spent a tremendous amount of time coming up with a subassembly, identifying where the risks were, so we were trading off the fact the company was not going to give us time later in the program or the money with, hey, guess what? We're going to use a ton of manpower up front to, to help compensate for that.
Okay, thanks.
Yeah.
Adam, there are a few questions on the chat box.
Yep.
So do you want me to read it out?
Yeah, could you read a question, please?
Yes. So Jim asks, what's the typical number of HALT sample size? What would be the cost of it? And looks like Jim has a difficulty in procuring the number of units to do HALT.
Yeah. So, I would say typically, as far as there's three parts to the cost. Three parts are the lab cost, so let's assume you don't have the equipment in-house. The second part's the fixturing cost, and the third part's the actual samples. So the lab cost, I would say typically 3 days of time. It generally ends up being under $10,000 in a lot of cases. Fixturing costs can a lot of times be pretty low because you're looking to simply clamp it to the table. But of course, if your product's more complex, the fixturing costs can be more complex. And then the big one, how many units do we need? Well, any amount's good, even my example of 0 units with the laser where we made something different. But really, as far as actual samples to test, between 3 and 5 is I would say the bare minimum, where you're not wasting lab time, the 3 days of lab time, because you are looking to induce failures. And if you just had 1 unit and you cause failures to where it can't operate at all, that's it, right? So I would say 3 to 5 is reasonable with parts and anything you can do. You think you need to keep them going, doing soft fails and backing off. But obviously, if the product's inexpensive, bring 50 of them because the lab time's expensive, right? So if your product costs $10 each to manufacture, don't show up with just 5 of them and have paid $10,000 for 3 days of lab time. Come with 50 of them because so what, right? And then just keep breaking them and getting as much damage as you can, break it in as many ways as you can while you have access to the chambers.
Yeah, there are a few other questions in the chat box. Adam, we can take one more before we move on to Chase part of the presentation.
Yeah.
Are there any simulation tools that we can use to expedite HALT testing?
So you can't do that. You can't use simulation tools, but they pair together. So you have to remember, simulation is based on knowledge you already have, right? That's where the boundary conditions come from. That's where the structure, that's where the elements come from. HALT testing is about discovering what you don't know from the real world. So they are the opposite and complementary because you then may be able to take observations from HALT testing and improve your model, and then do a lot of iterations in your model and take that new design and bring it back to HALT testing. So they're very complementary and work well with each other, but they're effectively the opposite. So that's great with the questions. I want to make sure Chase has time to share. He's going to share with us some really interesting experiences and observations he's had in all the years he's had, running Reliant Labs out there, which is an amazing lab. I highly recommend you reach out to him. And then just let you know, again, on Friday, the new book, The Perfect HALT Test, comes out, and you can get it on Amazon, and you can email me if you'd like an invitation to the book launch webinar on Friday. All right, so let's see if we can fluidly transfer this over to Chase. Chase, do you see the share option on your control panel?
Yeah, yes, I do, Adam.
All right, hit it. Let's see what happens.
Are we good?
Yes, it looks good to me.
Great. Yeah, thanks, Adam, for your introduction on HALT testing. My name is Chase Wers, and again, I'm the founder and co-owner of Reliant Labs. We were founded in 2002 by myself and my partner, Ken Duncan, and we're located in Sunnyvale, California. So we're right in the heart of Silicon Valley. Reliant Labs has always been specializing in HALT testing. So that's our main concentration is HALT and HATS. Our goal is to be the premier HALT lab and do HALT testing better than anybody else. We also just do standard, basically DVT, temp and humidity testing. And then as Adam mentioned, also just your standard ALT, RDT, thermal cycling and shock testing. Being here in Silicon Valley, we definitely have the biggest customer base by far. So we have 10 HALT chambers here. We have all of our HALT chambers are Qualmarks, and we have 3 different sizes. So you talked about when's a good time to perform HALT testing on your product. One of our main goals is, since we do have such a large amount of HALT chambers, we try to strive to be able to get customers in, on a short notice. So when they're ready, to start HALT testing, we have a chamber ready to go, so they can start when all those different things come together. So by far, we pretty much HALT test everything, but by far our biggest sector of customers that we have is in telecom and networking. Juniper, Palo Alto Networks, Arista, and Cisco. We test pretty much all of their products, all different types of servers and chassis from 1UI to 6-foot tall systems. So like Adam mentioned before, our customers use HALT as a quick evaluation to benchmark their new products and new designs versus previous generations. Again, it's typically about a 4-day is a typical HALT test. And a lot of our customers, like these big networking companies, like Pan and Arista and Juniper, it's just to give them a quick evaluation to make sure that the product is meeting the same levels as their previous generation products. A lot of our customers too use it as a comparative. So they might be manufacturing the same product at 3 different contract manufacturers. So they'll basically do a HALT as a quick evaluation to make sure that the Taiwan CM products have the same performance and the limits as the site in Guadalajara. A second way they use HALT is just comparative fixes, which I'll kind of talk about a little bit in some of my examples of some of the failures that we find. Is A better than B? So here's a very typical HALT setup that we use here at the lab on a 1U high pizza box. The fixturing, most of the times, it's very straightforward. We probably can fixture 95% of the stuff that we HALT test at no cost. It's just the materials we have at the lab. So again, like Adam mentioned, we always want to have the HALT product powered on and functional and try to get the best diagnostic coverage that we can. So just to give you an idea, these 1U high pizza boxes, we probably do HALT on these at our lab, probably 400 different variations of these a year. So we really do have a pretty good database of what we tested before. So the first, I'm just going to kind of go over 3 or 4 different kind of failures that we found at the lab. And like Adam mentioned before, the first thing is to analyze and really try to find the failure, during the HALT testing. It's pretty easy, with the high levels of stress that we use with the liquid nitrogen and the high power heating and the vibration. It's easy to make it to fail. It can be a little trickier pinpointing and trying to discover what the root cause of the failure could be. So in this product, like a lot of the other ones we have a pretty good history of what the products have done in the past. So even though HALT it's a test of failure process and it's not a pass-fail test, a lot of our networking customers have established some limits that they said, okay, we are going to test a failure, but if we have a failure that occurs, say between -20C, +60C, and at 25 Gs of vibration or below, we're going to consider that a must fix. That's something that has to be investigated and has to try to get to the root cause. So this is a vibration failure that we found during vibration step stress at what we consider a very low level of stress at 15 GRMS. So this was an SSD that was secured with a plastic clip that during the HALT test, during the vibration stress, we started to see these intermittent failures, and all of a sudden it would just see these intermittent reboots. And then what we did is we would take the fixturing off, we'd pull the top cover off on the chassis, and we found at the beginning that if you applied just a slight amount of pressure onto the SSD, it would slightly kind of seep back into the connector. So we were able to identify that this SSD was causing the intermittent problems. So if you gave it enough stress on the right, the SSD would completely pop out. So what they did is they looked at the original clip on the left that was securing the SSD, and the mechanical engineer came up with a different design where it kind of locked into place, and it wouldn't allow that SSD clipped. So when they came back with this improvement onto the chassis, they didn't have to completely redo the HALT. We just take it back and just repeat the vibration step stress, and then just prove that we don't see the same failure at 15 GRMS, and that it can work to a much higher level. This next example is kind of very similar. Again, it was just on a security appliance. This is something that we didn't see during the HALT test. It wasn't detected in the functional test software, but when we were doing the visual inspection, after a low level of vibration, we noticed that the little coin battery was backing out, and we haven't seen that before because we have HALT tested previous versions of this product in the year before, and we were kind of a little alarmed that it did come out at such a low level. The good thing about this failure is that the vendor was using two different types of these battery mounting clips. So we were able to basically compare vendor A versus vendor B, and they did discover that one clip actually held the battery much better at higher levels of vibration than the other one. So this is the kind of failures that you kind of see. Again, it's just a process of discovery. Suggesting the stress and see what happens. Definitely in HALT testing, we probably find our most relevant failures in the fourth and the fifth step when you are doing vibration, step stress, and combined environment. We have vibration with rapid temp cycling, but definitely larger components, heavier components on the board are more susceptible or more prone to failure. So again, our customers are just trying to see, just trying to get a good feeling that they're not going to see any gross problems at low levels of vibration. So again, I think this occurred at 20 GRMS, which we consider not that much stress. But here you can see, these broken leads on this inductor, which is about the size of like a quarter. Probably the biggest, I think, bang for your buck is just HALT testing on power supplies, which we do a lot of here at Reliant Labs. Just because, one, it's a pretty easy setup. AC power in to DC electronic loads. So it's a little bit easier to set up the product for the HALT testing. But the great thing about HALT testing on a power supply is that when you do find a failure, it's pretty easy to find the problem of it. You can pull out the schematics, and in a pretty short period of time, you can kind of pinpoint exactly what caused the failure that you discovered during the HALT. So in this example of a common thing that we found during the HALT is where the red arrow is, again, you kind of have this larger mass component of this big blue capacitor that's kind of mounted, right on the edge of the board. But if you see that lead, it's kind of rubbing up against that part. So right below the arrow, you can kind of see a crack where it fractured off during the vibration. And again, it's what level did this failure mode occur at? It was a pretty low level of vibration. So, the easy fix is just to go back to the power supply manufacturer, bring this to their attention, and then try to come up with some way that you can eliminate that abrasion of it rubbing up there. I'd say the most difficult one for last, but this was another networking product that we found kind of like a soldering problem on the PHY. So the main chip that kind of does the traffic routing within the system. But again, these intermittent problems can be the hardest to discover, but can be some of the most biggest changes that you can have at trying to feed back this information, to your CM. But here, basically, it was just a bad soldering job. So you can see on these pads where you kind of had a soft solder and a weak solder, but it was just causing like the intermittent contact, which was, causing, basic packet drop, packet loss. So those are kind of my 4 or 5 examples of kind of the things that we find here during the HALT tests. But I think the main thing, again, it's just our main goal in HALT testing is just a discovery. In that 4-day process is we're just trying to quickly feedback information to engineering and management so they can make a quick, good no-go decision that the product is ready for the next step.